All right, everyone. Very good to see you all here. Hope everybody had a good weekend. So today, as you can read, the focus is Faraday's law and electromagnetic induction. Now, this is one of my favorite lecture topics all semester because this is the last big piece of this puzzle of electricity and magnetism that we've been putting together over the past few weeks. So what I'd like to do just to start with is a bit of an overview for what the plan is for today and where we're going with this later in the week. So the plan for today, the real sort of meat in the sandwich this week that we're going to be focusing on is Faraday's law. So we're going to be working through what Faraday's law is and why it's so important. And we're going to be working through this in 3 distinct steps. Now, Faraday's law is the physics which is essential for understanding what's going on here in this beautiful picture of some wind turbines, some offshore wind turbines. So we've got the wind coming through here, turning the turbines, and up here we've got the generator, and that's converting that mechanical energy into electrical energy. And the physics that describes how that happens and the voltage that we're going to generate, that's all described with Faraday's law. So it's an absolutely essential concept in physics to making the modern world happen. And it also gives us some very profound insights for the relationship between electricity and magnetism. So I hope you guys all find it really interesting, and it's also super important for understanding the modern world. Now, once we've covered Faraday's law, we can see a bit more how it applies for electrical generators and also transformers. So 2 very important examples of Faraday's law in action. But before we get to Faraday's law, there's a few things that we need to cover, a few pieces of the puzzle we need to put together. So we need to be a bit more concrete about this concept of magnetic flux. What really do we mean when we're talking about all these magnetic field lines going all over the place? How strong are they? And there's this also very interesting concept there called Lenz's law. Nothing to do with optical lenses, very interesting property that we get when we're moving wires through magnetic fields. And before all of that, it's quite useful to have a bit of context by looking at electric motors. And also that's going to help to recap some of the concepts that we saw last week. So that's the plan for today and for the rest of the week where we're going with that. Now, before we dive right into the physics, just a bit of a heads up with this week, because this week is the most difficult week of the semester and of the year. So in terms of conceptually, it's pretty difficult. And also in terms of mathematically, it's also going to be pretty difficult. So if you're just worrying, oh wow, it just seems to get more and more difficult every week, just a heads up. This is probably going to be the most challenging lecture, or the most challenging week of the semester. So for the rest of the semester, we are going to see some concepts which might be more conceptually challenging, more conceptually interesting, but the math is pretty straightforward. We're only going to be looking at a few fairly straightforward equations, so the math is going to be fairly simple to work with. But whereas today, we have some quite tricky concepts. They're quite tricky to, you can't really visualize them. And also, we're going to be working through some of the crunchiest math that we're going to be doing all semester. So what I really encourage everybody, make sure you're logged in to Point Solutions. Really make sure you follow through everything that we're going through step by step, because we're going to be breaking Faraday's law down into 3 distinct steps. So really make sure that you're keeping up with each of those steps, because each piece of the puzzle is fairly straightforward. I know you guys will be able to manage each piece. So just make sure that you're keeping up as we go from piece to piece. And I'm sure you guys are all going to be fine there. So that's just a bit of a heads up about this week. So it is going to be pretty challenging. I'm sure you guys can manage it. And for the rest of the semester, it's actually going to be a bit more straightforward. Okay, now that's out of the way, let's start with a bit of a recap for what we saw last week and see how it applies when we're thinking about electric motors. So last time, one of the big things we saw was the relationship between the magnetic field and current and force. And we saw this right-hand rule here. Now, it's at a bit of a kind of awkward angle there. I think he's probably busted his wrist trying to do this demo here. But we can see what the force is on a wire if it's in a magnetic field. So we've got our magnetic field here, we've got a permanent magnet. So remember, magnetic field lines, that's represented by the fingers. I guess it looks a bit like fingers. And they go from north to south. So if you're following along, we want to line our fingers up north to south. And then the thumb points in the direction of the current. And this is when, yeah, it's kind of a bit awkward there. So the current is basically coming out towards us. So the current is going in the direction of all of you guys. And then the force comes out of your palm. So we can see from this that the net effect is going to be pushing the wire upwards. Now, if you try and do that fully, I think you're going to dislocate your shoulder or something, but you get the idea, right? So this is the right-hand rule for these three different directions, all at 90 degrees to each other. Now, if we just have a wire sitting in a magnetic field, that's quite interesting. You can put the current through the wire and it's going to move in the magnetic field. So that's quite neat. One of the things that really got me thinking, when I was still at school, and I thought, wow, this physics, that's pretty neat, that's pretty smart, that's quite impressive, is how this principle is extended to make an electric motor. Who studied electric motors before? I was like, okay, a few people. Okay, so the first time I heard about electric motors, I thought, wow, that's just really smart and really neat. I really enjoyed it. So we're going to see how this principle applies for electric motors. I hope you guys like it as much as I do. So if we have a wire like this is actually starting to look a little bit like an electric motor. Let's see how we can extend this a bit more. So we've got a coil of wire here. We've still got our magnetic field. So the field lines, they go north to south. Now this is all angled a bit more kind of comfortably. You don't have to bust your arm in order to get it angled. So follow along if you like with the right hand rule. So the fingers go north to south. Then the thumb goes in the direction of the current. So if we're looking at this side of the coil, the current's going upwards. So the force, it's going to be pushing the coil towards the screen. So we're going to be getting a torque on the coil. So we're getting the current from the battery, it's flowing around the coil, and that's pushing this side of the coil into the screen. But let's follow the coil around. So the current's coming up here, it's going along here, and then it's coming back down the other side of the coil. So this side, magnetic field's going in the same way, but the current's going down. So it's going to be pushing so the current's that way. See, this is what I mean about you've got to kind of be quite flexible to this. So the magnetic field's going north to south, current's going downwards now, so the force is going to be pushing the coil out towards you guys. So what we get is a twisting force acting on the coil, so it's spinning the coil around. So if we just had this set up and we flip the battery on, it's going to flip the coil around. So we're going to get some motion there. But that's only half the turn. It's not going to keep spinning. What keeps it going is this really snazzy little contraption here called a commutator. So if you look at how this coil is connected to the wires here, it's connected through this little piece of equipment here, which switches as the coil rotates. So once the coil's rotated, it rotates and comes around, and then the current basically gets flipped because this commutator is flipped over, so then the current's flowing the other way. So once this ring has flipped around halfway, then we're back to here, and it's going to just keeps on pushing round and round and spinning round and round. And that's an electric motor. So I thought that was really neat how this just one little piece of equipment here, which is connecting the current from the battery to the current in the coil, keeps the whole thing spinning. And that's a very simple electric motor. Now there's things you can do to make this all more efficient, make it work a bit better, but fundamentally that's what's going on with an electric motor. So really nice application of that right-hand rule. Now that's what's going on with an electric motor when we're taking some current and passing it through a magnetic field and using that to get motion. What we're going to be thinking about for the rest of the week is essentially doing the opposite process. So we're putting in the motion, so maybe with some wind turbine, something like that, and we're moving something in a magnetic field and using that to generate our electric current, which is what's going on in a power station. So we're going to be thinking about the physics of how that works. Before we get to that, we need to be a bit more specific with exactly how we're quantifying how much magnetism we're talking about here. So we know if we have permanent magnet here, we've got some field lines, they're going to be going north to south. We need to get a bit more concrete with exactly what we mean when we're talking about the strength of the magnetic field. So I've got a diagram here. There's quite a bit going on in the diagram. Let's not worry too much about it for now. We'll unpack what's going on bit by bit and see what's going on here. The main thing I want to start with here is we've just got some magnetic field lines here. So we use the letter B for magnetic field. So we've got some magnetic fields and they're all kind of going in that direction. So let's just worry about that for the time being. Now, if we're looking at how strong the magnetic field is, previously we've been thinking about the magnetic field in terms of what we technically call the magnetic flux density. And we measure that with units that we call Tesla. So whenever we see B for the magnetic field, specifically what that means is it's how strong is the magnetic flux density. Now, that sounds quite technical, but what it means is how many magnetic field lines, how densely packed are these magnetic fields per area. So we're going to unpack this a bit more, break it down a bit more, and see exactly what this means. So it's the field lines per area. But when we're thinking about electrical generators, we need to think about the total amount of magnetism. And we measure that in units, they're spelled like this. It's pronounced a bit more like Weber's, sort of rhymes a bit like sort of Darth Weber because it's a German name. Who speaks German in here? I'm probably murdering the pronunciation. How should it be pronounced? Weber.
Yeah, well, that's more Frenchy, yeah. It's like,
More Frenchy, okay.
Yeah,
If we were just going for just German? Weber. Weber, okay. I mean, I'm going to murder it either way, but you guys know what I'm talking about here. So, Weber.
That was really good.
Did I say it all right?
No, you said, oh, I'm going to murder it. And I just went, yes, but I didn't mean it like that.
No, that's quite all right. I'm sure I am. So, anyway, the symbol is a WB. Maybe I should just stick to that. So where were we? Webers. Okay, so it's a unit of magnetic flux. So what's the difference between magnetic flux density and just magnetic flux? Well, the magnetic flux density is how many of these lines we have per area. So it tells us how tightly or loosely these magnetic field lines are. But these Webers, I've just kind of all over the shop with his pronunciation now. It's the magnetic flux multiplied by the area. So we use a B for the magnetic flux density, and we use this Greek capital letter phi for the total amount of magnetic flux. And you can think of the magnetic flux as the total amount of magnetism. So maybe we have a low magnetic flux density. Maybe we don't have a very strong magnet, but maybe in our electric motor, we've got a big old coil. We've got a really big spinny coil. It's still going to get quite a lot of magnetic flux. Or if we have a really strong magnet and a much smaller coil, we could get the same magnetic flux. So we just multiply the magnetic flux density by whatever the area is, and that tells us the total amount of magnetism. Now, we can think a little bit more about what's going on with this diagram because, they've got the angle here, this theta, and over here they've got the flux. It's BA times cosine theta. So all this means is that if our magnetic field lines are going perpendicular through the area we're thinking about, then we can just multiply them both together. So that's where we just get the BA. So if that's our B perpendicular to the surface. But if our magnetic field, if we bring that all the way down here and it's parallel to our surface, then we're not going to get any magnetic flux. So you might see it written a couple of different ways, a bit like what we saw last week, right? So we can either write this rule like this, where it's our B with a perpendicular, or we can write it like this with our B and the cosine theta. They just mean the same thing. And if you do ever see it written without the perpendicular or with the theta, it just means we're assuming the magnetic field is perpendicular to the surface. That's what's going on there. So we've got with our units, so 1 Weber is equal to 1 Tesla meter squared. I think that's... So the last thing about this situation, which is really important whenever we're thinking about electric motors or electric generators, is remember with our electric motor, we had that coil of wire that was spinning around. So in that example, we just had one piece of wire, it goes up, it goes around, and then it comes back down again. But if you want to make your electric motor a bit more powerful, or you want to make your electric generator a bit more powerful, what you can do is you can wrap multiple coils of wire around your area. So if you look in an electric motor, has anybody done this scene inside an electric motor or dismantled one, anything like that? So it's not just one piece of wire, you've got loads and loads of bits of copper wire all wrapped around. And the reason is because every loop of wire picks up the same magnetic flux. So for every loop of wire you can fit in, you're going to pick up that much more magnetic flux. So what you might see written is, if we have n coils of wire in our motor or our generator, then our magnetic flux, we just take this and we multiply it by n. So our magnetic flux is just n times the magnetic field times the area. So that's a bit of an overview of the relationship between magnetic flux density, which we saw last week, and total magnetic flux. So we just take the flux density, multiply it by the area, so however big the coil in our electric motor or our electric generator is, and however many coils of wire we have there. Now we're nearly ready to start thinking about the physics going on in an electric generator, which we describe with Faraday's law. Before we get to that, there's one last really important principle, really interesting principle that we need to unpack before we're ready to get to Faraday's law. And this is Lenz's law. So it's a really neat idea, a real nice bit of symmetry here. So we saw last week that if we have current in a wire in a magnetic field, that's going to cause a force. So something that physicists like thinking about a lot is symmetry of a situation. So what would happen if we come along and exert a force on a wire? So I got this little diagram over here. We've got some magnetic field lines. So there's our magnetic field going from north to south. And I've got a piece of wire here. And I'm trying to indicate the wire it's going, across in this direction, into and out of the screen. So we know that if we passed a current through this wire, there's going to be a force exerted on it because it's sitting in a magnetic field. But what if, instead of passing a current through, we come along over here and we exert the force on the wire ourselves? So what do you reckon's going to happen? Because we've come along and exerted the force on the wire, what we actually get is that we've generated the current. So if we think, okay, well, this wire has some length L, if we assume that our force is perpendicular to the magnetic field, then the force we exert, it's just this BIL that we saw last week. So last week we saw that if we have a wire of length L with a current of I in a magnetic field of B, it's going to have a force equal to this. So if we do the opposite, if we come along and exert this force, we're going to be producing this current, and that's what Lenz's law tells us. So we can rearrange this equation and we can solve for I. But the really interesting thing we get from Lenz's law is that the current that we're going to make opposes the force. So let's see what this means. If we take our right-hand rule over here, so we put our fingers in the direction of the magnetic field, and then the force is going upwards. So from the direction of our thumb, we would think from this that the current's going to be coming out from the screen towards you guys. But because we've come in and exerted the force ourselves, the current's going to be opposing that. So the current's going to be going in the opposite direction. So the current is going to be going in towards the screen. And that's what's going on with this minus sign over here. So we've just rearranged the equation and then we pick up a minus sign because the current is going in the opposite direction to what we would expect. And that's the fundamental idea with Lenz's law. So it's a really important law when we're thinking about turning some mechanical work into electrical current. Now this is quite an inconspicuous little setup. We're going to come back to it a few times as we're working up, as we're building up towards Faraday's law. Now if we suppose we've moved our wire some distance that we call delta x, we can start to think about how much work have we had to do to move this wire. So I've got a question here. We know what the force is from what we saw last time. We know that we're going to have to be exerting a force of B times IL, where I is the current that we are producing. And we've moved that wire a distance x. So how much work have we done in moving this wire? So let's see what everybody thinks for this one. I'll take a look at the results in just a moment. So remember, work is force times distance. We know what the force is and we know what the distance is. So hopefully for this one, we're just putting these two pieces of the puzzle together. This is going to tell us how much work we need to do to move this wire a distance of delta x. Okay, very good. Let's take a look at the responses. Let's see what everybody thinks for this one. Okay, so some people going for all of them. Looks like most people going for option B there. So remember, so work is force times distance. So we're exerting a force over some distance. We know this is the force. We know this is the distance. So when we combine them, it's got to be option B over there for the amount of work we've got to do. So very well done, everybody, with this question, especially if you got that it's option B. So we've come along, we've gone and moved our wire up through the magnetic field, and we have done BIL delta X of work. Now this is actually a really important result when we're starting to build this line of thinking towards an electrical generator. So let's see where this goes. Now, if we think about how much work we've done, let's just recap what we saw. Okay, so we've got a wire of length L, we've moved it a height delta X. So the work that we've done is BIL delta X. So it's just the force multiplied by the distance that we've moved the wire. Now something's really interesting. If we look at exactly how we've moved the wire here. So the wire, it's got some length L and it has some distance delta X that we've moved it here. So we can actually think about this as an area. In moving the wire from here to here, we've essentially swept the wire out over an area. So maybe we could have had a wire that's half as long and then we move it for twice as far. That's going to give us the same area. So it's quite a creative way of thinking about the work done here, because this L times our delta X is actually giving us an area. So area, it's just L times delta X. So we can rewrite this equation in terms of a change in area. Now, if you're following along in the notes, you don't need to wait for it to go up on screen. You can have a go yourself. What we see is that the work, it's just the magnetic field times the current times the change in area. So we've just generalized this a little bit. We can have a longer wire, we don't have to push it as far. We can have a shorter wire, then we have to push it further. I think it's a really nice geometric, creative way of thinking about this situation. Now there's one last simplification we can do to really cook this down into a very neat functional form here. Because remember when we were looking at magnetic flux and magnetic flux intensity. So if we've got our area here and this magnetic field in terms of B, well, B times our area, that's going to be our total magnetic flux. So remember, magnetic flux, it's just B times our area. Now, if we're keeping B the same and changing our area, we can simplify this even more. So our work done, it's just the current times the change in the magnetic flux. So maybe if our magnet was half as strong, if this B was half as strong, then we'd have to move our wire twice as far to get the same change in magnetic flux. So what I like about this is we've gone from quite a specific geometric situation up here, where we need to worry about how long our wire is, how strong our magnet is, how far we're moving it. And by thinking about the geometry of the situation and the magnetic field, we've reduced it down. We've just got that the work we've done is equal to the current times our change in magnetic flux. Now this is a super important piece of the puzzle when we're thinking about how electrical generators work. So if you're following along in your notes, you probably want to at least underline this equation because it's really quite important. We're going to be coming back to it quite soon. Now this is when we can start to mix in some physics connections, because we know we've come along and done this amount of work on the wire. So we've exerted a force over a distance, we've done some work. And we know that energy is always conserved. So we've gone and done some work. Where's the work gone? What's happened to that energy that we've done? Well, we know from Lenz's law that if we've gone and done some force opposing the current, we've gone and moved some current through the wire. And that's what's happened to our energy. So for step 2 of Faraday's law, we need to think about relating these two. So we know some things about power in general. We know that power is always how much work we've done divided by how long it took to do it. And we know from a few weeks ago when we were thinking more about current and circuits, so power in a wire, it's just the current times the voltage. So with these two pieces of the puzzle, let's see what do we get when we put them together to relate how much work we've done to the voltage that's going on in the wire. Now this might seem a bit of a tricky one because we're thinking quite generally in terms of power and energy and work, but we know power, it's just energy per time, and we know that specifically in a wire, power is current times voltage. So we're just setting them equal and we're solving for the amount of work we have to do. So if you're not too sure about this, give it a go of working through the algebra. Once you work through the algebra, it actually really helps to make a bit more sense and see what's going on here. Okay, very good to see those responses coming in. Let's take a look. Let's see what everybody thinks for where this energy has gone. What does everybody reckon here? Okay, so some people going for all of them. So really all we're doing here, we're setting these two powers equal to each other. So we know that IV is equal to work divided by delta T. We're solving for work, so we just multiply by the delta T. And what do we get over here? We get option D over here. So where's the thing coming? Up. There we go, got there eventually. So work, current times voltage times our delta T. So how long it took to move the wire. So if we come and do this work of moving the wire, this is what's going to be the effects of the current and the voltage in the wire. So these are the two, this is the second big piece of the puzzle that we need for Faraday's law. So in step 1, we saw how much work we've done on the wire. Now we've seen what's happened to that work in terms of what's going on in the wire. So we're ready for step 3 of Faraday's law, putting these two pieces of the puzzle together. So let's just recap step 1 and step 2. So the work done by us, we've come along and done an amount of work equal to the current that we induce from the wire times that delta phi times the change in magnetic flux. And then that energy has gone into doing work in the current in the wire. And it's equal to minus IV delta T. And it's minus because we've come along and done the work, and then that current is opposing it. Okay, so it's moving in the opposite direction. So with these two pieces of the puzzle, let's put them together and solve what's going to be the voltage that we induce in the wire due to the work done, due to the fact that we've moved that wire in the magnetic field. If you're not sure about this one, remember we've just got these two equal equations for the work done by us and the work done on the wire, and we're just setting them equal and solving for what the voltage is. So if you're not too sure, give the algebra a go, set them equal, solve for the voltage, and see what you get. Okay, very good to see those responses coming in. Let's see what we get. What's the voltage that we get if we're changing the magnetic flux in a certain amount of time? What does everybody reckon here? Okay, so nobody's going for B or D. Some people thinking C, some people thinking A. So when we set these two equal, so the current's going to cancel, and then when we solve for V, it's going to be delta phi divided by delta T. So option A over there. So very well done, everybody who gave this question a go, especially if you got that is option A. So let's just summarize these three steps, put everything together, and recap everything that we've seen. So if we have this situation, we've got a wire in a magnetic field, and we're exerting a force on it, then the voltage we're going to get in the wire, it's equal to minus the change in magnetic flux divided by how long it took us to do that change. So if we move that wire delta x in a certain time, well, if we halve the time, so we move it twice as quickly, then that's going to change the voltage that we're going to get in the wire. Now, as it's written here, we're thinking about maybe a big change in the magnetic flux, and maybe that's going to take a certain amount of time. But this relationship, it's true whatever the scale of the changes are. So if we just have a small change in the magnetic flux in a small amount of time, that could give us the same total voltage when we look at the ratio. So in physics, we usually use a delta, capital delta there, the triangle, to mean a big change. If we're just thinking about a small change, we use a little d over there. So if you've done calculus, you'll have seen this kind of notation before. So we can just write out exactly the same equation, but instead of for a big old change with a capital delta there, we can just write it with a little d. So we know that the voltage is equal to minus d phi by dt. So very well done, everybody who put those pieces of the puzzle together and worked it out. Because this is Faraday's law. This is the very famous relationship that Faraday discovered, the relationship between changing magnetic flux and the voltage that we're going to get in a wire. So very well done if you figured this out for yourself. Now, in practice, when we're having a setup like this, we want to get some voltage. So we're going to be having to change something in a certain amount of time to get this changing magnetic flux. Now, usually we're not going to be changing that B, so how strong our magnet is. You know, if you've got a generator, we're going to have some magnet there and something's going to be sitting in there. So the way that we change our voltage is by, the way we change our magnetic flux is by, in practice, changing the area. So changing that magnetic flux is going to generate a voltage, and we usually call that induced electromotive force. So it really is a voltage. We're inducing a voltage in the wire, but there's lots of ways you can get a voltage. You know, you can connect your circuit to a battery. That's not necessarily induced electromotive force, but what this means is we've done some force of motion, and that's induced a current in the wire. So if you hear people talking about induced EMF, they just mean the voltage in a wire due to what's going on with your generator. Now, let's just think a little bit about some applications of this. So we know from Faraday's law, so that induced EMF, the voltage, is equal to minus d phi by dt. Now I remember from, it wasn't quite the first slide, but at the beginning of the lecture, so our magnetic flux, it's equal to the area, so how big our coil is, B, so the strength of the magnetic field intensity, and then N, so the number of coils of wire we have. So if we're making an electrical generator, we want to put the whole thing in a nice big strong magnetic field. We want to have a nice big area, make it as big as we can. Sometimes those things are kind of difficult, but the easiest thing to do is just to wrap lots of coils of wire around our generators to make that N nice and big. Once we've done that, maybe we're going to spin the whole thing. That's not changing the number of coils. It's not changing what the B is. What that is effectively doing is changing our area. That's how we kind of generate voltage in practice. So have a think about this question. What's our induced EMF going to be if we're only changing the area of our coil? Let's see what you think for this question. If you're not sure about this, start from Faraday's law there. So the voltage is equal to minus d phi by dt. And we know the magnetic flux is phi equals NBA. But we're keeping N constant and we're keeping B constant. The only thing we're changing is A. So think about how you could write that as an equation where A is the only thing that's changing. Okay, very good to see those responses coming in. Let's see what we get. What's our induced EMF going to be if we're changing the area? So everybody reckon. Okay, so some people thinking maybe D. Looks like most people going for option A there. So if we take this phi is equal to NBA, substitute in for that induced EMF, we know that the N is constant, the B is constant, we can kind of move them out, and we're just left with this option A over here. So voltage is equal to minus NB dA by dt. So very well done everybody who gave that question a go. So what that tells us is if we're thinking about making an electrical generator, we've got some coil of wire sitting in a magnetic field, and the faster we can change that effective area that's cutting across those magnetic field lines, the more voltage we're going to get. So very well done everybody who figured that one out. Now last slide for today, just like to take a bit of a kind of graphical overview of everything that we've been thinking about today and see how everything relates, and hopefully kind of summarize and wrap up everything that we've been thinking about today. So we've got our situation over here, and this is a very, very schematic diagram of an electrical generator. So we've got our magnetic field here, so we've got our magnetic field lines here. And then this is a top-down view of a coil of wire sitting in that magnetic field. So it's really a very similar setup that we had at the beginning of the lecture with the electrical motor, where we had a coil of wire in the magnetic field. It's just this time, instead of connecting that coil to a battery making it spin, we're going to come in and with some mechanical means, so maybe ourselves or with a wind turbine, we're going to turn this coil in the magnetic field. And then let's see what that does to the voltage we're going to be generating. So to start with, we need to be thinking about the area. So here, our coil is cutting right across the magnetic field. But as we turn our coil, it's going to go parallel to the magnetic field. So our area goes from being some maximum area, and then as we turn it 90 degrees, our area goes down to nothing. So have a think about what's that going to do to the voltage that we're going to be inducing in our coil. So remember the relationship between voltage and area that we just saw. So a voltage minus NB dA by dt. So it's really related to the slope of how this area is changing over here is going to be our voltage. So even though we start off with some area, our voltage actually starts out really low, and as we're changing this area, that's giving us some voltage. So even though by the time we get to the fact that there's no area, because our area is changing, because we have this slope here, that's what's giving us the voltage. It's the rate of change of area, not how much the area is. So then if we keep spinning our coil over here, our area is going to go back to a maximum. And then even though our area is a maximum, if we look at the slope here, the slope is actually flattened off. So the slope's flattened off, so our voltage is back down to 0. So that's the relationship between what the area is and what the voltage is. And then as we keep turning, finish one cycle, there's always that relationship between the area of our coil and the voltage. So we can relate that with a bit of calculus. If you've done the calculus, you know, the derivatives of sines and cosines. If you haven't done those before, that's fine, to just have a bit of a sort of understanding of the relationship between the two. Now, this is the fundamental principle behind generating electricity in something like a wind turbine. You have to have a permanent magnet, you have a coil of wire, and then you turn it around, and that's going to give you the voltage. So that's the fundamental physics principle. Now, next time, we're going to be thinking about some of the practical considerations that we need to be thinking about to be actually making an electrical generator and also distributing it over an electrical grid. So we're going to be using the ideas from Faraday's law that we've thought about today and really see how they work in practice when we're making an electrical generator and an electrical transformer. But for today, that's a great place to wrap things up. Very well done today with the questions. Really well done. I'm so glad that you guys kind of followed along because it can be kind of tricky. Just a reminder, everything's back on as usual this week. So we've got the lecture Friday as usual, and also we've got the workshop tomorrow afternoon. So I hope you guys have a great afternoon, and I'll see you guys all in the workshops tomorrow.